Okay guys, so today we're going to be talking about sigma notation and how it relates to calculus. So sigma is just a Greek letter. You can see it up here in the first line, right there. And what it means is the sum of the values when we plug in each of the integers from the lower bound to the upper bound. So in the problem that I have right here, this I, that's called the index of summation. We can use any variable for that index. And generally speaking, I use an x, just because that's the variable that we're used to using. But in your book, they're going to use an index of I sometimes, n sometimes, k sometimes. They use a lot of different values, variables rather, for the index. So you also need to understand what it means. So when we see I here, then we're trying to find the ith term of the sum. So a sub 3 would be the third term of the sum. A sub 4 would be the fourth term of the sum. And then this number is called our lower bound and our upper bound. So what this means is that we would plug in all of the numbers, all of the integers from 1 to n. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. If n is 11, then I would stop at 11. And then these are called the terms that we get, and we would have to add them all together. So let's look at some examples here of how we would work this on this first one. So we would have to plug in 1 for k, 2, 3, 4, 5, 6, and add them all together. So let's go ahead and do that. If k equals 1, if I plug in 1, 3 times 1 is 3, minus 4 is negative 1. If k is 2, this is addition, so I'm going to plug in 2 now. 3 times 2 is 6, 6 minus 4 is 2. I have to plug in k equals 3. So 3 times 3 is 9, minus 4 is 5. I have to plug in 4. So 3 times 4 is 12, 12 minus 4 is 8. To plug in k equals 5. 3 times 5 is 15, minus 4 is 11. And I have to plug in k equals 6. So 3 times 6 is 18, minus 4 is going to be 14. And so the sigma notation tells us that it's a sum, so that's why I wrote it out as pluses, and I just have to add it. So it's 25. 25 plus 8 is going to be 33, plus 5 is 38. And then that would just be 1, so the answer would be 39. And you can add them up in any order, of course. All right, so for number 2, the only difference here is that instead of using a k, now we're using an I. We have a new function that we're using. We're using I squared plus 1. So again, we plug in 1. 1 squared plus 1 is 2. We plug in 2. 2 squared is 4, plus 1 is 5. We plug in 3. 3 squared is 9, plus 1 is 10. 4. 4 squared plus 1 is 17. And 5. 5 squared plus 1 is 26. And then we have to add up all of these numbers. So this is 17 plus 17, that's 34. 34 plus 26 is going to give us 60. So finding the sums here, it wasn't too difficult, but that was because we had a small lower sum. So we only had to plug in 6 values here and only 5 values here. But we're going to get down into problems where the upper bound could be 100. And in that case, we're going to have to either use our calculator or we'd have to use some summation formulas. But before we do that, let's look at how we can go from the other direction. So now we're going to use sigma notation to write out what this sum would be. So it's 2 squared plus 3 squared plus 4 squared plus 5 squared plus 6 squared plus 7 squared. Well, I can write this then as the sum, and I can start this however I want. I can start this at x equals 1, x equals 2, x equals 3. The lower bound can be whatever I want it to be. It'd be easiest to make it equal 2. Because then what's our function going to be with respect to this x? What's happening to the x here, here, here? squaring it, right? So my function would just be x squared, and then what's the integer that we're stopping at? 7. So that would be the way that I would use sigma notation to write the sum. But what if we had been told that our lower bound had to be 1? How would that change things if our lower bound had to be 1? Any idea now of what the function would be? I can't just do 1 squared because it starts at 2 squared. Anybody know? Raise your hand if you think you know. Michael? Right, it's going to be x plus 1 quantity squared. But am I going to keep the upper bound as 7? What's it going to be now? 6. So both of these would be ways that we could write the sigma notation to represent the sum. For number 4, looking at this, 3 times 2 over 5 plus 1 plus 3 times 3 over 5 plus 1 plus 3 times 4/5 plus 1 plus 3 times 5/5 plus 1. This looks very complicated to write in sigma notation, but it's really not. This 3 is never changing, is it? So I know I'd always have a 3 here. Now, we should decide where we want to start. Do you want to start this at 1, or do you want to start it at 2 or 3, or what? What do you think would be best? Okay, Peter says start it at 2. Okay, and then Peter, can you think of what would have to go in here then? Right, it'd have to be x over 5, and then plus 1, that's happening every time. And then where would the x's stop at? 5, right? So this would be one way to write it. But sometimes we're told that our lower bound has to be a 1. How would that change things if it had to be a 1? Any ideas of how it would change? What would our function need to change? Can I just plug 1 into this and get those values? What do we have to do to x to get those values? Add 1, right. So it's going to be 3 times x plus 1 over 5 plus 1 now. And what is our upper bound going to be? Is it still going to be 5? What's it going to be now, everyone? 4. So both of those would be ways to write that in sigma notation. All right, so here are some very popular summation formulas. This one says the sum of the integers from 1 to n is just going to, of a constant, is just going to be the constant times n. A lot of people don't understand what that means. Let me show you. That would mean I have the sum, and let's say as I goes from 1 to 7 of 4. That would be the way it would look. As we go from 1 to some constant, up to some value of the constant. So what that means is if I plug in 1, I get 4. If I plug in 2, I get 4. 3, 4, 5, 6, 7. I have to have 7 terms because I use the integers from I equals 1 to I equals 7. But it's always a constant value. So look at this, 1, 2, 3, 4, 5, 6, 7. Doesn't it make sense that to do that, it's just going to be the constant times n? Okay, so that one's not difficult at all. The next one, I always like to think of it like this. It's going to be, it's saying that if we're trying to add up certain integers from 1 to, say, 10, or 1 to 20, or 1 to 30, and we're going to add those up, like 1 plus 2 plus 3 plus 4 plus 5. We're using all those values. This is the formula we can use. N times n plus 2 divided by 2. So it's really going to be n over 2 times n plus 1. You can do it that way as well. All right, let me show you what this is saying, though, a little bit better. So there's a story about a mathematician whose name was Carl Friedrich Gauss, and he was alive during these years. He went on to be a very famous mathematician. You've probably heard of some laws that he's made up in science, and he did a lot of work in mathematics, but he ended up being a very famous mathematician. So the story goes, when he was in 3rd grade, his teacher was always trying to keep him busy because he was one of those kids. She would give him a set of math problems to do. He'd be the first one finished. He would be finished in 10 or 15 minutes with the assignment. All the other kids, it took them a couple hours to do it. So she wanted to keep him busy, so she said, okay, Carl, I want you to add up all the numbers from 1 to 100. So she thought he would sit there and do 1 plus 2 plus 3 plus 4. You know, add up all of these. In the middle would be 50 plus 51 plus ... And then here at the end it would be 96 plus 97 plus 98 plus 99 and plus 100. And she thought, okay, that's going to keep him really busy. She thought he would just do it in order. Like 3 plus 3 is 6, that's 10, that's going to be 15, etc. But he comes back within a couple minutes and he tells her the answer. And he says the answer is 5,050. And she's like, okay. How did you get that? So then he shows her how he figured it out. Here's what he did. He did 1 plus 100, that's going to be 101. He did 2 plus 99, that's going to be 101. 3 times 98, that's 101. 50 and 51, that's 101. So what did he do then? If he had all these values that added up to be 101, how many of them would there have been? There would have been 50 of them, right? So he did 101 times 50, and he just realized that that's going to be 5,050. And so that's how he came up with the answer so quickly. He didn't take the time to literally add up all of these numbers. See, the key to doing well in math and even on the ACT a lot of times has to do with noticing patterns. Like he noticed that this pattern held true, that if he added up the first number and the last number, these two, and then paired them up like that, he was going to have 50 pairs of 101. That's really what this formula is. It says we're going to do n over 2. So n over 2 in this case, we had 100 terms. So n 100 divided by 2 is going to give us 50. That's going to tell us how many pairs we have. And then 100 plus 1 is 101. So see how that's going to be the same thing? He was really using this formula without ever being told it. Okay? But I just think that's really interesting how a lot of those early mathematicians, they were, instead of doing things just the rote way that most people would do them, they would find shortcut ways. And so this summation formula is kind of always attributed to him because of that story about him. All right, then we have these other summation formulas that we could use. And if we were going on to take like the AB calculus test, we would have to have all these memorized and use them in order to find area. Because calculus is really, integral calculus is this. We have some kind of curve. We want to find the area under the curve. So one way to do that would be to make rectangles under the curve. And then find the sum of the areas of all of those rectangles. And see, the smaller these rectangles are, the more accurate that area is going to be. So what happens is we want the sum of all of these areas. So the sum of the areas. Now, what would we want the width to be in order for it to be the most accurate? We want the width to be as small as possible. So theoretically, we want it to get as close as possible to what number? If you want it to be as small as possible, what's the smallest it could be? 0, yes. So we would want these widths to be infinitely small. And that's where calculus started with the whole concept of an integral. is making these rectangles infinitely small, adding up the sum, and that would tell us what the area is. And that's what we're going to talk about later, is how we can use these rectangles to help us define these. So the sum of all of those areas would tell us the area under the curve. If we find the integral, that's the same thing as doing that. And that's why we study integration. All right, so we're going to get to that in a few minutes. That's the reason, though, that we're learning the whole summation concept, is because of that. It's a sum of all of those areas. Okay, but here are the types of things we want to be able to do with summation. We want to be able to do a problem like this. Get out your calculator, because we need to see if your calculator will do this the easy way or the more difficult way. All right, so if you have a newer calculator, you are a lucky person, because you can simply go to math and you can arrow up and you can find summation right there. And all you have to do is plug this in. I never use i's because then you have to go to the i's that are in blue. So I'm going to put in x equals 1 to 20 of 3x. And I don't have to use all those formulas because my calculator will tell me it's 630. Okay? So how many people have the summation on their calculator? All right, so quite a few. But some of you do not. If you do not, then this is the way that you have to type it in. And I'll show you how to do that. We have to find sum on the calculator. Everyone has this catalog button. And when you get into college level math, you might need to find something, and everything on this calculator is located under the catalog. So go to second 0, and you're going to see a list of everything. If I just start scrolling down, it's going to take me forever to get to the S's. So I can jump to the S's simply by pushing this key right here, because that's where the S is. Now it jumps down to the S's, and I can go down to sum. So we want the sum, all right? So we push sum of the sequence. So now I have to find sequence. So I go back to catalog. I want to jump to the S's again. And I want the sum of the sequence. And then I have to tell what is my function. My function in this problem is 3x, comma. Now I have to tell it what is the index. So the variable that I'm using is x, comma. I have to tell it the lower bound 1, comma. And then I have to tell it what the upper bound is, 20. And I don't think you have to actually put that. That's telling you the increment. It's telling the calculator to go up by 1 every time. But I think it still works if you just close the parentheses and hit enter. It does. Okay, so you can forget about the 1. That's not going to really be necessary. We're always going to go by 1, and that's what the calculator knows. All right, so anyway, so this is 630. So that's going to be a lot easier than trying to use these formulas. But I just want you to have seen these summation formulas in case you have to use them later on in your next calculus class. All right, so let's look at the following one. We need to find this sum. Now, those of you who have it on your calculator, you're just going to go to math, you're going to go to summation, and you can just type it in. All right, but let's say you don't have it and you want to go back to that catalog again. Well, here's the nice thing. Let's say that I've done some other math, and I want to go back to what I did before. On these older calculators and the newer calculators, I can push second enter. And that's going to take me back to the last problem. But just push second enter again, and it takes me back to the one before. Second enter again, and it takes me back to the one before that. I can sit here and do this until I get back to things that I did a long time ago. But see, now I can just edit this. So I want to tell it what is the function, and my function is x squared plus 5, comma. My index that I'm using is x, I'm going from 1 comma to 20, and now I can push enter. And it's 2,970. Okay? Everybody able to find that? All right, so now let's look in our book about how this whole summation is used in calculus. So I'll put it up here, page 262. All right, so for this, we're trying to find the upper and lower sums. So like I was saying earlier, we're trying to find out the area of this shaded region. When those early mathematicians, and the two earliest mathematicians to work on calculus were Sir Isaac Newton and Frederick Leibniz. They were the two that first started thinking about derivatives and integrals as a way to find instantaneous rate of change with derivatives, an area under a curve for integration. So what they started with was, they said, okay, I want an estimate of this area. So they did what's called the lower sum. They would take this rectangle, see how it's bounded by the curve right there? So that's called a lower sum. So I'd have to find that area, then I go up. This would be the next one I would talk about right here. That would be the next value for the lower sum. Then I keep going. This would be the lower sum. And then on this one, that would be the lower sum. So the lower sum means that I'm always staying underneath the rectangle that I'm finding. I'm staying underneath the curve. So what is this area right here, guys? Just this rectangle here that I'm drawing. It's 1 in width, 1 in height. So what's its area? 1. So to do this then, to find my lower sum, it's going to be 1 plus, and then I have to go to the next rectangle, and the next rectangle is going to be a height of this, and it's still a width of 1. So what's that height right there? See how that height's 3 for that rectangle? So this is going to be 3 times 1. So that area is going to be 3. And then I go to my next rectangle, and you can see that its height is 4. So it's 4 times 1 is its area. So it's plus 4, plus, and then on my last one, I have to stay under the curve. So it's going to be right there, and that height is 4.5, so it's going to be plus 4.5. So the sum of those areas is going to tell me my lower sum. So 1 plus 3 is 4, plus 4 is 8, plus 4.5 is going to be 12.5. So that's going to be what's called the lower sum, when we stay under the curve. And the lower sum gives us a nice estimate, but it's not a great estimate. So then Newton and Leibniz, they said, hey, what about if we find the upper sum? Okay, so now they looked at the rectangles that are going to be above the curve. So looking at this first space, let me blow this up so you can see it a little better. So looking at the first spot here, the upper sum is going to be where the shaded region intersects the curve. So here's where the shaded region intersects the curve. So now I'm talking about the area of this rectangle. That rectangle right there. What is the area of that rectangle? 3. And then I go to the next rectangle. It's going to look like that. What's that area? 4, right? Go to the next one. Oops, I went too high. It intersects right there. So this area is going to be 1 times 4.5, so that one's 4.5. And then my last rectangle, I look at the shaded region, I look where it intersects. The last one is this. So to find the upper sum, it's going to be this first area, which was 3, plus this area, which is 4, plus this area, which is 4.5, plus the last area, and that last area right there is 5. So my upper sum then is going to be 7, that's 11.5, plus 5, 16.5. That would be the upper sum. Okay? Now, even though these are just estimates of the area, they still have specific answers. Like the lower sum is 12.5. It's an estimate of the area, but that is exactly what the lower sum is. And again, upper sum, same way. This is an estimate of the area, but the answer for the upper sum is 16.5. What do you think would even give us a more accurate representation of the area? What could I do with these two numbers to find an even better estimate for the area? If this one's always too small and this one's always too large, what could I do with the two of them? Average them, right. So what's in the middle of 12.5 and 16.5? 14.5. 14.5 would probably be a very good estimate of the area under that curve. Okay? So you guys are going to do some problems like that. Let me just show you real quick on this one. The lower sums. Here would be one of them. Here would be the next one, because we have to stay under the curve. For the next region, it would be like that. And then for the last region, it would actually be 0. See how the lower sum for this one right here, I can't even make a rectangle if I have to intersect the shaded region and that curve itself. So you got to think about all that stuff. All right, questions? Okay, so you guys have your assignment up there. You can go ahead and start on that.